everyone, welcome back. Welcome back. Today we are going to talk about ReLU activation function. ReLU stands for rectified linear unit. And now, what is an activation function? So, friends, when you come back home and if it's dark, what do? You come, you turn on the lights. Okay, you turn the switch on, you activate it. What happens? Once you turn on the switch, the light gets on. Okay, there is light in the room wherever you have turned the switch on. Here it's similar, but here we do not have light. In a neural network, what do we have? We have neurons, we have layers, and we have neurons in the layer. The layer consists of neurons, right? Here, see, each one, this one, these are the layers, these are the inputs though. These are the layers. Each layer consists of neurons. Now, when I say the word neuron, what comes to your mind? What is a neuron actually? A neuron is nothing but a mathematical function. It's just a function. That's a neuron. And a layer, each layer is nothing but a collection of these functions. And very, very simple function, nothing complex. Each one, what it does is receives the input from the input layer. The input could be features and weights, and it sums them and adds a bias to it, okay, based on the weight. And then it uses the activation function to decide whether to propagate the value that it has received to other neurons or other functions, or not to propagate, just stop the value right there. So if the feature is not important, it will think, okay, I should not forward or I should not send the output of this computation here. You see this? This is nothing but a summation sign. So a neuron is nothing but input multiplied by the weight plus the bias. Okay? And it's the sum of all the inputs multiplied by their respective weights plus some bias. And activation function will help decide whether to propagate it further or not, whether the feature is important or not. Okay, so this neuron, the function, based on the value of the summation, it will decide, okay, do I pass this message along or do I stay quiet? Don't worry, at the end of the video, we are going to see a example in Python of how it is done. Okay, so as I explained before, what are activation functions? They introduce non-linearity, okay, which means non-linearity means, see here, it's not necessarily the path of activation is this. It could be this, this, and this, right? The value of this could activate this, and then this outputs this. Or the output could be this, this, this. So it's non-linear. Linear means in a straight line. So non-linear means it's not a straight line. So because see, let's say if this stops, if this function decides, no, I don't have to propagate, then the output from this here, it will stop here. But the output of here, this neuron will continue and then pass on. So it's non-linear. It depends on the value, the sum value. Okay, so Here it is. See the summation, weight multiplied by the input value plus the bias. And then we define the activation function. So this is in short one neuron. Like that, in a layer, you will have hundreds of neurons, okay, and hundreds of input parameters. Rather, it could be billions of parameters, okay, lots and lots of parameters for real life training. Let's say for image detection in for car driving, right? There are so many things on the road, not just one parameter or two parameters. There could be thousands and thousands. Like there could be a sidewalk, there could be a divider line. If it's a freeway, there could be multiple lanes, there could be other cars, other vehicles, some people walking, animals walking. It could be so many unlimited things. It could be rain coming down, so that also it has to see. So multiple features are inputted into this or could be inputted into this. Okay. So in short, what are activation functions? Whatever the sum value the neuron computes based on the weight and input and the bias that is passed to it, this function will decide whether to send the output or not. That's in simple. Okay. So there are multiple activation functions. Like there is a sigmoid activation function, there is a ReLU activation function. Okay. We're going to talk about sigmoid later. ReLU is the simplest form. Okay. So if you see what is ReLU, max of 0 or whatever the input is passed, the maximum of the two. So if the input passed to it is negative, it returns 0. If the input passed to it is anything greater than 0, it returns just simple that value. It's that simple. Okay, so you can see the input of this could go here, could go here, 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 and here finally. And this one is based out of the input of this and this neuron. Okay, two neurons are inputting into this, passing on the weights here. Okay, so this is non-linear, right? You have seen this. So the path goes from here. This is the input layer, goes here, 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 here. Okay, and then these two combine here. So multiple neuron passes their output to the other layer neurons. So each one is a neuron. Each one is a layer. So let's say if this is a feature map. If a feature has a negative value after computation, it turns to 0. If it is greater than 0, it leaves it as it is. It's as simple as that. See, all the negative values are converted into zeros. The positive values or greater than 0 values are left as it is. They're very efficient. Okay, mitigates vanishing gradients. That's a different problem. Sparsity, it can lead to sparse activation whether if many neurons output the value 0. Okay, so if if there are too many negative weights, okay, assigned, because weights are chosen randomly in the beginning. So if too many negative weights, then a neuron can or a function can all be always dead. Okay, it might never get activated. So that's a sparsity. That's one of the problems, which is called as dying ReLU problem. So this, in order to overcome the dying ReLU problem means if the same weights and same input is sent to a neuron and its value always comes to 0, then that neuron will never activate another neuron. So that means we are technically killing that neuron. So in order to overcome that, so we add a little bias, which is called as a leaky ReLU. So in this, what is done is, how in the previous example we saw it's 0 comma x. If it is 0, we just add a tiny bias. so that the value remains positive, okay, and it's not always negative. Now in this, the tiny value is fixed, so let's say 0.01, so it will always be fixed. There is parametric ReLU and flexible ReLU. Parametric ReLU means you pass the value what you want to add to 0, okay, the bias value, you pass it. Flexible, it depends, it learns on its own, okay, how many times the negative value is and all. So that's flexible ReLU. Different variations. So like see, leaky ReLU 0.1 if it is 0 or x, okay. Parametric ReLU, you multiply it by some fixed past parameter value, maximum of either this product or the actual value whichever is given. So that is about ReLU, activation function. Now let's see it in an example. Okay, so here we have our simple ReLU function. Okay, as you can see, we are using the NumPy library, NP maximum of 0 or x, whichever is the maximum. So we are not using parameterized ReLU or leaky ReLU. This is a simple ReLU function. Only thing what it returns is whatever you pass to it, it will return the maximum of 0 or that number. And this is our layer where you give inputs, you give the weights, give the biases and the activation function. Okay, that defines the neuron. So inputs inputs to the layer. So example, it could be the output of the previous layer. Okay. Weights connecting the inputs to the neuron in this layer. Shape should be inputs twice. Okay. So the weight should be for every, it is 2D. Okay. So that every neuron of the previous layer gets connected to the every neuron of the current layer. Biases, again, random biases that is added. Activation function, right now for this example, it is ReLU, and it returns a number array, a NumPy array representing the output layer. Okay. So you initialize the linear output. NP dot dot means you compute the dot product of inputs multiplied by its respective weights, and you add the biases. If activation function is there, it calls the activation function and passes the output, which is nothing but the sum, right? Dot products plus the bias. Usage. So you're passing the input data. You define number of neurons, three neurons. So the 3 circles. Input data dot shape, okay, which will give you 3. You initialize the random weights. You initialize random biases. You choose random because initially it has to be random, and then the model learns and tries to adjust the weights. And here is nothing but output. You create a layer and the output with the ReLU activation function. So it's as simple as that. But this is not done in practical life. This was just to demo how to create a layer, how to create a neuron, and how to create a ReLU activation function. In real life, what happens is you use inbuilt library. You use TensorFlow library, and here see you define number of neurons, activation function. You don't have to define your own ReLU function or anything. You use the inbuilt function which is available in the TensorFlow library, in the Keras. Okay, you have the layer, you have the input shape, everything is available. You have the model, compile the model, and you get the output layer model.predict. Okay, this is how you do it in real life. The previous example was for you to help you visualize how in the backend, if you say model.add these layers, the activation function, the input shape, what is happening behind the scenes. So this was the example. Well, hopefully it's a little bit clear to you. What is ReLU activation? What is a neuron? What is a layer? How to create, what goes on behind the scenes when you create a layer using some available Python libraries like TensorFlow and other libraries. Okay. All right. Thank you all for your time. Next time, we will talk about sigmoid activation functions. Thank you for your time. Feel free to like, subscribe, comment, whatever you feel like, your choice. Thank you. See you all again next time. Until then, have a wonderful, wonderful time. Bye.